Okay, so in this video, we are gonna prove that the norm of the Legendre polynomial p sub n of x, that norm square, is basically 2 over 2n plus 1. And the fact that it works for any Legendre polynomial, that's awesome, right? And yeah, in this video, we are gonna prove it for any general p sub n of x that its norm square is 2 by 2n plus 1. That will be the goal of this video. Before I start, you can see that here, you can see a picture of Legendary over here, right? He seems to be angry, I don't know why. Yeah, and just before we go, let me just tell you about what is Legendre polynomials are actually. So yeah, initially, Legendre polynomials were defined to be the solutions to this differential equation as you see over here. 1 minus x square y double prime minus 2xy prime plus n times n plus 1 y equals to 0, right, for any positive n. And yeah, the solution for, let's say, some n that is defined to be the Legendre polynomial p sub n of x, right? And there's already a general formula. This is called Rodrigues formula, which is a general solution to this differential equation, right? P sub n of x. And using this formula, you can actually get all these Legendre polynomials, right? Just substitute n equals to 1, 2, and go on. And you can get all these polynomials, right? And now there's actually an interesting property of Legendre polynomials that makes this famous, right? The fact that all these Legendre polynomials are actually orthogonal to each other. So what I mean by that is, basically orthogonal means if it's vectors, then their dot products are equal, right? And in terms of function, the inner products are equal. Basically, inner products of p sub n of x and p sub m of x, basically that's always 0. Let's define the inner product as integral from -1 to n, right? And p sub n of x, p sub m of x dx, right? And yeah, I mean, orthogonal means the two vectors are orthogonal, right? Like, I mean, yeah, if their dot product is 0, right? Similarly over here, if these are two different polynomials, right, not the same, because for orthogonality we need two different vectors. Yeah, in the similar way, if their like inner product is 0, we say that these two polynomials are orthogonal. And it's interesting that actually for Legendre polynomials, if n is not equal to m, so any two like different Legendre polynomials are always orthogonal, and their inner product, as we see here, is always 0, right? Again, now just like in the case of vectors, like we knew that inner product with itself gives us magnitude, right? Magnitude squared, right? So yeah, inner product with itself, we know that this actually gives us magnitude square, right? And this one is just integral from -1 to 1 of p sub n square of x dx, right? Now this one is always 2 by 2n plus 1. And yeah, our goal is to be able to prove that thing, that the magnitude of this Legendre polynomial is always 2 by 2n plus 1. And that's an interesting thing, right? So yeah, while proving this, we'll also use this fact that Legendre polynomials are orthogonal to each other, like two different Legendre polynomials are orthogonal to each other. We are going to use this fact. We will be able to prove this. And yeah, so let's start the proof now. To prove, we will actually use the generating function of Legendre polynomials. There's actually a really nice generating function. Yeah, let's say if I take this generating function, right? Basically, so where n goes from 0 to infinity, and then this p sub n of x, and then t to the power n. Note that these are different. So this one is actually equals to 1 by square root of 1 minus 2xt plus t square. Yeah, we're going to use this fact. So let's also introduce another, like let's introduce two different like sums, right? So that we can have two different Legendre polynomials. Also notice that the interesting thing is this thing over here is completely independent of basically any. It doesn't make sense. Yeah, okay. So what I'm actually trying to say is, yeah, this just depends on x and n, and that does make sense because this is actually a function of x, right? So yeah, just that. Okay, now Let us also introduce another sum. Now this time let's say it goes from m equals 0 to infinity. What I was trying to say is, like, even though those two might seem different, I mean they're actually same. Yeah, so they will have the two different such expressions, right? We can just take product of them. Sorry, we can just take product of them. Yeah. So now this gives us 1 by 1 minus 2xt plus t square is just sum goes from n equals to 0 to infinity, sum goes from m equals to 0 to infinity of Pn of x, Pm of x, t to the power 2n, right? Now we'll just take integral of both sides from -1 to 1, right? Because we know that we want to make use of the special properties of Legendre polynomials, right? For different indices, if there are two different indices, these are just orthogonal. We want to make use of that. So for that, let's just integrate both sides from -1 to 1, and then with respect to x, right? We can take the integral inside the sum. So if we use that fact, what we get is integral from -1 to 1 of Pn of x, Pm of x dx, right? And then t to the power 2n. Now there's an interesting thing over here. So we can do this integral. Basically, this integral is in terms of x. So this is actually just a linear function in terms of x. So that will just be ln of 1 minus 2xt plus t square by -2t from -1 to 1, right? Over here, notice that whenever n and m are different, this integral is just going to be 0, right? Because two different Legendre polynomials are orthogonal to each other, right? So what we're gonna do is, we know that this is gonna be non-zero only for both m and n being same, right? So we can actually write it as single sum n equals to 0 to infinity, right? And then during that time, we know that whenever these both of these n are same, this is just gonna be okay. So this is just gonna be integral from -1 to 1 of p of nx squared, right? So, and basically we know that this is just the norm, right? So, or I can write it as just the norm. See what I mean? And we don't need dx now, and t to the power 2n. So yeah, what happened is, only when n and m are equal, it actually is not 0, right? So for all those n's, we know that when n and m are equal, we are gonna get the norm of the polynomial. So yeah, I'm just writing the norm of polynomial times t to the power tn, right? So this side is simplified. This side is, I think, almost simplified. Now let's try to do this limits. So here at 1, this is ln of 1 minus 2t plus t square by -2t minus, and this becomes ln of 1 plus 2t plus t square by -2t, but that makes it plus now. And this is just sum from n equals to 0 to infinity of the norm of the Legendre polynomial t to the power 2n. Now we can take 1 by 2t common, and this becomes ln of 1 plus t whole square, right? And I can take that for in division by 1 minus t whole square. I'm just using rules of log over here, right? So I took this first and divided by that, because log of a by b is log of a minus log of b, right? Sum from n equals 0 to infinity p n of x squared t to the power 2n. Now this just becomes now I can use the squares to, I can take the squares out and then cancel with the 2 over here in denominator. So that gives us 1 by t ln of 1 plus t by 1 minus t, right? And this is sum from n equals to 0 to infinity of norm. Yeah. And now I can actually expand the log as sum. What I'm trying to do is, actually, if I get sum over here, then you can compare term by term, right? So that's what I'm trying to do. Now this becomes sum from n equals to 1 to infinity, and then 1 to the power n plus 1 t to the power n by n, right? Minus, okay, so minus minus, I mean, yeah, basically let me take plus, and then I will have negative ln of 1 minus t with me, right? So again, that is a really good sum expression. So it is sum from n equals to 1 to infinity just t to the power n by n, right? And this is sum from, basically I could have written this as single sum actually, right? It wouldn't really have mattered. Actually, if I'm writing it as two different sum, I should have written different indices. But yeah, I can actually write them as same sum, so it doesn't matter. Yeah, okay. So now sum from n equals to 0 to infinity Pn of x t to the power 2. Now notice that over here in this sum, what's happening is basically for all the, when n is even, this index is odd, and that makes them cancel out, right? So we only need odd ends, right? So what's happening is we only need odd ends, and only then it doesn't cancel out, and there are actually two terms which will add up, right? Because it odd end, this is even, and this just goes to 1, and they add up. That will be 2 times t to the power 2n minus 1. So 2n minus 1, at n equals to 1, this is 1, right? And 3, 5, yeah, this works. And then 2n minus 1, right? And then this is just sum from n equals to 0 to infinity of the norm of Pn of x squared t to the power 2n. Now, if I also write this from n equals to 0 to infinity, what I get is 2 by t sum from n equals to 0 to infinity t to the power 2n plus 1 by 2n plus 1 is equals to sum from n equals to 0 to infinity its norm t to the power 2n, right? Now I can divide by t, which gives me 2 times, let me take the 2 inside, sum from n equals to 0 to infinity 2 times t to the power 2n by 2n plus 1 is equals to sum from n equals n to infinity Pn sub x squared to the power 2n. Now if you just compare term by term, we can see that this implies Pn of x square is equals to 2 by 2n plus 1. And that actually proves the fact that the norm of all the Legendre polynomials are actually 2 divided by 2n plus 1. And that was indeed an elegant proof, right? So we basically invoked the fact that these are orthogonal to each other, and also their generating function, and also the definition of the inner product for functions and their norm. And yeah, so with this we proved the fact that for all Legendre polynomials it's 2 by 2n plus 1, and because of which you can see that the results are also consistent. 2 over 1, 2 over 3, 2 over 5, 2 over 7, all these are consistent. So once we have proven for the general n, now we don't need to prove for any other n's. It's proven for all of them. So that's it. I hope you enjoyed the video. Thanks for watching. I look forward to seeing you in the upcoming videos too.